All right, welcome. So today we're going to talk about the relationship between integrals and derivatives. So this last class we evaluated some integrals using antiderivatives. So that probably solidifies sort of in your head this idea that like an integral is I almost wrote the word derivative. So an integral is an antiderivative. Those are basically the same thing, which then sort of like makes you think like, well, an antiderivative, that's like undoing a derivative. So that like sort of leads to two big ideas here, like integrals undo derivatives, and likewise derivatives undo integrals. They're sort of inverse processes, which sticks with the theme in math, because in math, every time you learned about something, you learned about the thing that undoes it. Addition and subtraction, exponentials and logarithms. So this just sort of keeps fitting with the theme. And so why is that true? Well, we're going to actually do a little proof of why that is true, because it wasn't obvious to actually some ancient mathematicians. They actually were working on integrals and derivatives separately, and it took a few years before they realized that they're actually the same thing, or at least they share the same universe. So to do this, we're going to think about a very generic function, f of x. It's been a while since I've done this proof, so I might have forgotten how to sort of go along with it. So if I get stumped, you get to hear me sort of struggle as I go through this. So we're going to think about the derivative of the integral of this function f. So we're going to do both at the same time. So here we go. We're going to go the derivative of the integral of the function f. We're going to go, let's see here, what's a good way to think about this? Yeah, just the derivative from, I don't know, whatever, a to x, let's say, of f of t dt. So t is going to be representing sort of the inputs along here, and we're specifically, so I should probably change this to a t. That's the t-axis. So we're looking at like, hey, what is the derivative of the integral from a to x, where x is our sort of changing input. So a stays put, and then x sort of just gets changed. Okay, so, well, there's really no other way to sort of do this other than to think about the limit definition. I think that's where we're basically at. So here we go. We're going to go limit as h approaches 0 of the integral of f minus the next one. I am infringing upon my graph. Uh-oh. Okay, all over h. Okay, so if this looks a little bit funky to you, the thing to focus in on here is that the input is x. So what I've done here is I've made the first input x plus h. The second input stays x. So this is following that same form of a derivative where h approaches 0, where it's like it was f of x plus h minus f of x. So I'm doing the same thing here. Okay, so let me put this on the graph. The integral from a to x plus h. So I have here the integral from x to a to x. X plus h would be just a little bit to the right of that. Assuming h is a positive number. It could technically be negative, but we're going to assume it's a positive number for this. Okay. Well, so we are finding the difference in these areas. So what is the difference? Well, the full area is from a to x plus h. that represents this. This area here is just from a to x. So we can actually rewrite that entire numerator using just a single integral, because that just means actually all we're interested in is this area here. So let's do it. So it'll be the limit as h approaches 0 of the integral from x to x plus h of f of t dt all over h. Okay. Now, we want to try to represent this area a little more cleanly. And the cleanest way, actually, is to think about it as a rectangle. As h approaches 0, this x plus h moves towards x, and ultimately, you end up with just a perfect rectangle where the height of it is this point here, x comma f of x. And so the height of that rectangle is going to be, we're going to keep doing this. Limit as h approaches 0. F of x, that's the height of the rectangle. And the base length is just the difference between x plus h and x. Well, that is h. So times h, base times height, all over h. And so now we can divide those h's, getting us that the limit as h approaches 0 of f of x. And since there is no h in our function anymore here, we can evaluate that limit by just getting rid of the limit. So there you have it. The derivative of the integral of f is just f. You'll notice that there's been a variable swap out. So x being the input here, now we use x instead of t. But there you have it. The derivative of an integral, they undo each other, leaving you with just the function you're interested in. So, shazam. All right. So, let's see this in action. Where can you use this? The answer actually is not in many places. It's got some lame examples that you can use this for, but I'm going to show you how to do the examples two different ways to make sense of it, to connect together sort of the two ideas from last class and then this video. So we're going to do this example, which is not an interesting example at all. We want to find the derivative of this, okay? You could tell I messed up in places. So if we take literally what the above told us, we can do this problem very quickly. So here it is. You want to find the derivative of it. So this is approach number 1. And it's the least interesting approach. Approach number 1, g prime of x. You want to take the derivative of the integral. All right. Well, according to this above work, the derivative of the integral is really just your function with that input into the input here. So in other words, it'll be 1 plus x to the 4th squared, since that's the input. Since the inner function here, x to the 4th, is actually a different function other than x, we have to use the chain rule here. So it's that, and then times the derivative of x to the 4th, which is 4x cubed. Or in other words, more nicely, we could write this as 4x cubed times 1 plus x to the 8th. So it's just this function, plugging in this thing. Got to use the chain rule, though, because this x to the 4th is actually the inside function. And so taking the derivative, you must do that. So that's just applying exactly what we learned here and using the chain rule. But you might be wondering, like, is this consistent with what we learned in the previous class? So let's go ahead and take a look at a different approach that uses what we learned in the last class. So this will be approach number 2. So what we learned in last class is that if you want to find a definite integral, you use the antiderivatives. So we're going to do that first. So we're going to find the antiderivative of this. So the antiderivative, I'll rewrite it here. So 0x to the 4th, and then 1 plus t to the 2nd dt. Okay, So the antiderivative of this is going to be t plus 1/3 t cubed. And we're going to evaluate that from 0 to x to the 4th. Okay, so if we substitute in here, we're going to get x to the 4th plus 1/3 x to the 4th cubed minus, plugging in 0 gets us 0 plus 0, or 0. So in other words, it is just x to the 4th plus 1/3 x to the 12th. Am I doing that right? I'm doing that right. Okay. So that's evaluating the integral. The original problem, though, says you should take the derivative of that. So this thing here represents g of x, and we want to find g prime of x. So if we do that, we get 4x cubed plus, that'll be 4x to the 11th. And they're not written in the same form, but if we factor, we can see that this will be equivalent to 1 plus x to the 8th is what we got inside there. So they do end up being the same answer. So either approach is okay. I'm going to be honest, I'm not going to ask this question too much of you because it's kind of lame. If you've memorized this little fun fact, it's super easy. Otherwise, you got to go through this whole mess here. So, but it is an example and maybe shows up on the AP test. I don't know. But I think the fun stuff is actually this, the fact that we can actually find the derivative of an integral, thinking about it graphically, and ultimately show that, yep, the derivative of an integral, those two things undo each other, leaving you with just your function. So come into class ready to sort of utilize this relationship, not through boring examples like this, but maybe more interesting examples that we can get our hands on.